second. Good afternoon, class. And today we're going to be continuing linear functions 3.2.
Thank you.
With Will I am.
All right, so we're still looking at linear equations. We're just going to look at a couple different things, couple word problem kind of things that are going to come up on the test. So first thing we're going to look at is what does it mean if you have a solution, okay, to something like that. Okay? A solution means if you tell me two numbers, give me a number for x, give me a number for y, when I plug it in, I get a true statement. Right? So somebody give me any number you want for x. X?
68.
68. Okay? And give me a different number for y. Noah? 11. If that's a solution, then that means when I plug in 68 for x and 11 for y, the answer would be 8. Is 2 times 68 plus 3 times 11 going to equal 8?
No.
No, too big. So what that means is these numbers are not a solution. Can anybody give me something that would be a solution? Okay. There's literally an infinite amount of answers. Okay. Some are easier to think of than others. Yep. If x is 2 and y is 4, if you plug in 2 times 2 is 4, 3 times 4 is 12.
Oh, no, I was thinking, no, sorry. I'm sorry, guys.
Let me start you guys off with one. Let's try 4, 0. Okay? If you plug in 4 for x, what's 2 times 4?
8.
8 plus what's 3 times 0?
0,
3 times 0?
0.
And then 8 plus 0? 8. So that number is, or that point is one coordinate that makes it true. How about this one? Let's try 1, 2. If you plug in 1 for x, what's 2 times 1? 2. What's 3 times 2?
6.
6. What's 2 plus 6?
8.
8. There's another coordinate that makes that true. Right? Any questions on that idea? So there's two ways we could ask this on the test. One way, we just say, tell us a coordinate that makes it true. Or we give you a coordinate and say, does it work? Now, if you were to make a list of a bunch of solutions that make this true, not just these two, but let's say you had 10, 11, 12 solutions. If you were to graph every solution that you came up with, all the solutions would be on a straight line. That's basically what the picture of all the solutions looks like. So the graph of an equation that has two variables is all the different points that you could plug in and it would make it true. And if you graph enough of them, the points are going to be so close together, eventually it's going to look like a solid line. Any questions on that idea? The graph of an equation with two variables like that is a straight line. That's what we're trying to show you.
Just a graph with two variables.
Yep. No exponents. No. Remember how Mr. White said no funny stuff. Yep. That would be a function. Yep.
Okay, I didn't know that.
All right. So the next idea we're going to look at is what's called discrete versus continuous. Has anyone ever heard those words before, like as they apply to math? Discrete and continuous?
I have.
You have?
Yeah.
All right. Do you know how to explain it, or it's a little tricky? A little tricky. All right. So let me give you guys an example. Let's say,
That's really wobbly.
if you want to, if you want to sit behind.
Hey, so
So here's an example of something that is continuous. Let's say you have water. Okay, you got a pot of water, it's on the stove. And the water is at room temperature. And you start to heat the water up. Okay, let's say you heat the water from room temperature up to boiling. As the water goes from room temperature all the way to boiling, what temperatures is it going to go through in between? If it starts at room temperature and goes to boiling.
All the numbers between them.
All the numbers, right? So if something's boiling, let's say room temperature was 70 degrees, boiling is 212. As it goes from 70 to 212, it's going to go through every single possible temperature. 80, 81, 82, 83, 84. When you're heating it up to boiling, you can't skip from like 85 to 90, right? It's got to warm up continuously. That's an example of something that's continuous. Discrete would be something like, let's say you were counting the number of people in the room. 1, 2, 3, 4, 5, 6, 7, 8. As I count, did I count every single possible number that exists between 1 and 8? Like, did I include everything? Fractions, decimals?
No.
No. Okay, I didn't. So that's an example of something that's discrete. Discrete means there's gaps, right? As I counted the people in the room, 1, 2, 3. I didn't count 2.6, 2.7, 2.8, 2.9. I skipped all those because that doesn't make sense. But when you're boiling water, if you were at 70, you would hit 70.1 degrees, 70.2, 70.3. You'd hit every single possible temperature. You wouldn't skip any. So that's the big difference between discrete and continuous. Discrete, you skip. Continuous, you don't skip. Okay, and we'll try a few more examples, and you're just going to have to figure out, is it discrete or continuous?
I didn't hear it in math, I heard it in science. And
Oh, in science?
yeah, there's thing like discrete, I'm pretty sure it was discrete, it was like the trail mix, and then another one was a bag of M&Ms. I mean, not M&Ms, it was a bag of almonds, and then the other one was like mixed trail mix.
And they just described it that way. Okay. All right, so let me show you an example of something that is discrete. I'm going to graph all the numbers from 1 to 5. I don't really need 0. Right. There's 1. There's 2. Notice each time I'm doing this, I'm lifting my pencil. If I lift, or whatever I'm writing with, if I lift what I'm writing with, I'm skipping stuff. Right? 3. Skipping everything between 3 and 4. Skipping everything between 4 and 5. That is discrete because you skipped things. You skipped 2.1, 2.2, 2.4, 2.7. Okay? Anytime you skip and you only have certain numbers, that's discrete. So if you were buying t-shirts at a store, can you buy any number of t-shirts you want in math, like any single number you can think of, or can you only buy like whole numbers of shirts? You can only buy whole numbers. You can buy 2 shirts, you can buy 3 shirts. You can't buy 2.7 shirts. So buying shirts in a store is discrete. You can't buy any single number you want, only certain ones. Certain ones, certain numbers. All right. So continuous. So continuous, that's where it includes everything. Anything you want to include. Let's graph all numbers from 1 to 5. Not just integers. Integers don't include decimals, but let's graph every single possible number we can think of between 1 and 5.
Very loud.
Yeah. I guess I write kind of hard on the board sometimes.
It's okay.
Okay, thanks. All right, so somebody give me a number between 1 and 5.
3.
3. Okay, so we're going to graph that one. Another number.
4.
Do you
Okay.
want decimals or fractions?
It can be anything.
Any number between 1 and 5.
1.5.
1.5. So the point here is if you graph everything between 1 and 5, you have to graph every single possible number you can think of.
Yeah.
It's continuous. How do I know? Watch as I draw it. Am I lifting my pencil?
Yeah.
I lifted my pencil with what I just did. As I started here. Did I ever lift? Fred? No, I didn't lift. So if I don't lift up when I'm sketching it, that's continuous. What if we were counting how many textbooks are on the shelf? Would that be an example of something that's discrete, meaning you only have certain numbers, or continuous? Could be any single number you want. Gemini? Exactly. If you're counting textbooks on the shelf, you can count 1, 2, 3. You can't count 2.6, 2.7. You can't pick any number you want, only certain ones. So continuous includes fractions, decimals. Discrete, there's gaps. Okay. Let's look at this one. So what we're going to look at is how to graph a function if they give you some values. Okay, they're going to give you certain values. And part of this is going to be deciding, did they give me something continuous or did they give me something discrete? Can somebody summarize what does discrete mean again? Yep, Jack?
Specific numbers.
Exactly, specific numbers, only specific numbers. Like if I had to pick a number of nights to stay at a campground, I can't just pick any number I want. I can't stay 2.6 nights. I can stay 2 nights at the campground. I can stay 3 nights. There's nothing in between 2 and 3. You either stay or you don't stay. That's discrete. All right. So how do you graph a function if they give you values in the domain? Step 1, we're going to make a table. Okay. We did a table like this, I think in the notes, in a homework problem a couple nights ago. Your first column is X. Your second column is a formula. Your third column is Y. And your fourth column is a coordinate. I think this was the last one in the homework.
And the function, right, like that second column there, it's going to be given to you in the problem. We'll say using the function, whatever. All right? So in that third column, basically it's going to be it's going to be the answer from the second column.
All right, so first thing you're going to do is set up a table, just like you did in the homework. Next thing you're going to do is you're going to look at this last column, and you're going to graph all the points that are in that last column.
Guys, we make a graph one just to show you how it works, but tomorrow on the test, you're not going to have to graph them.
And then the last thing you have to do is decide, based on the word problem, is this a discrete problem, meaning only certain numbers, or is it continuous, like boiling a pot of water? It's going to go through every single temperature from where it started to where it finished. It cannot skip.
Same thing, just like money, right? Money would be considered continuous, right? So you can have like $1 and like 5 cents.
Well, with money though, could you have any amount you will want? Like, is there an amount between $1.05 and $1.06? Like, is there an amount between this and that?
No.
No. There's no fractions of a penny. So in that case, money would be considered discrete because you cannot have any number you want. Only certain numbers. Okay? Any questions on that? All right. So let's go through and try something. So this problem says the linear function y equals 15.95x represents the cost for buying X tickets to a museum. Okay, we're buying, let's think about that. We're buying tickets. Can you buy any number of tickets, like any possible number you can think of in your head? No. You can only buy a whole number of tickets. You can buy 2 tickets, you can buy 3 tickets, but you can't buy 2.4 tickets. Doesn't make sense. So when we get to the discrete part, we'll write that down.
And guys, in this problem, right, we talked a little bit at the beginning of class yesterday about independent and dependent variable. So in this problem, what's the independent variable? Anybody tell me raising their hand? The independent variable. Talked about yesterday a bunch at the beginning of class. One of the values will be the independent variable, one of them will be the dependent. You just gotta know which one's which. Someone take a shot at it. It's okay if you get it wrong. Madison?
X is independent.
Yeah, X is independent, Y is always dependent. Or the thing you're plugging in is always the independent. The thing that comes out of it, or your answer, whatever it equals, is gonna be a dependent. Because it depends on what you plug in to get that answer. That's why it's called dependent. So X independent, Y dependent.
So in this case, what I would say, if we're going to word it that way, is the cost to go to the museum depends on how many tickets you buy. The cost is dependent on the number of tickets you buy. So first thing is find the domain of the function.
So guys, remind Mr. Hager, what's the domain again? What values? Someone tell me by raising their hand. Gemini? The X values, right?
And what are the X values in this problem?
How many?
What does X represent? Yeah?
X is the tickets.
X is the number of tickets. So what would make sense for how numbers of tickets we could buy? There's only, and keep in mind, there's a limit. So it's not like you could say, oh, we could buy 50 tickets. Can't go that high. We could buy how many tickets?
Like the number, like 1 through 4.
1 through 4?
Or like certain.
Is there any other number of tickets we could buy? Technically, there's one other number of tickets you could buy. Yeah? 0? Yeah, you could buy 0 tickets.
Go on and say, hey, the cost is too much, I don't want to buy any.
Now, would 1.7 make sense for the domain? Can you buy 1.7 tickets? No, if you go to the window and say, I want 1.7 tickets.
Number.
They're just going to look at you like you're crazy.
They're going to look at you like you're crazy. Okay? So, because you cannot buy any number you want, only certain numbers, is that discrete or continuous? This is discrete.
Now, guys, just, we're not going to do it, but just, can someone explain to me, if I wanted to get the range, how would I do it? How would I get the range for this problem? Think about what we just said in all the steps. How would I get the range? Range stands for what again? What values? The Y values, right? How would I get the Y values in this problem? What would I do? I have all my X's. If I look at the function in the problem, Y equals 15.95X, how would I get the Y's? What would I do? I have all my X's, and I see an X in the problem. What can I do? Mallory, what do you think?
Well, Y is in dollars, so we'll do the amount of the tickets.
We know the number of tickets, right?
Yeah.
What do you think you know?
Yeah, we know. We want more tickets.
But how? Go ahead, Gemini.
You would like plug in the numbers.
Exactly. Just play. So you'd have, in this case, you'd have 5 separate problems. Right? You plug in all of those. 15.95 times 0, 15.95 times 1, 15.95 times 2, 15.95 times 3, 15.95 times 4. Each one of those answers that you get are going to be your Y values, and that will be your range. So tomorrow on the test, we may ask you to find the range. That's what you have to do. Plug in each number, and the answer that you get will be your range.
All right, so let's do that, because we're going to graph this function now using its domain. So the directions say to make a table. What are my 5 X values? Yep, Xander?
0, 1, 2, 3, 4.
Yep, I need 4.
4, sorry.
So 0, 1, 2, 3, 4. Okay, and now my formula, Mr. Roy just said it, y equals 15.95 times x. So these are my x's. Now let's write it up. Y equals 15.95 times 0. 15 15.95 times 1. 15.95 times 2.
Oh, I thought we were supposed to solve it.
We are. Times 3. 15.95 times 4. Now, in the next column, that's where we simplify what we just did in column 1. So the first one's not bad. What's 15.95 times 0?
0.
That means if you buy 0 tickets, it will cost you $0. What if you buy 1 ticket? 15.95.
All we're doing is multiplying.
If you buy 2 tickets,
31.90.
yep, 31.90. If you buy 3 tickets, just add another ticket.
47.85.
47.85. Yep, you got the last ones.
Since when do you become smarty pants? Simple multiplication. Or 63.80. 63.80. Not hard. Simple.
So there's our
It's good. No, I like it.
there's our y value. And now, to graph it, you're going to graph these coordinates. 0, 0. Okay. The next one you're going to graph is 1, 15.95. Then you're going to graph 2, 31.90. 3, 47.85. And you're going to graph 4, 63.80. Now, those y values are bigger than we normally have, so I'm going to have to scale my graph. What would be good values to go by on my y-axis? So I can fit all those on the grid.
Is it 2? Is it 1? Is it 115? Is it 115?
1, 15.95. Yeah.
What would be good values to go by on my y-axis? I mean, there's no definite wrong answer. I just have to fit all those points when I scale. But Jack, what do you think I should go by on my y-axis?
63.80.
So you want to count by, what do you want to count by?
I'm gonna go by 5, I'm gonna go by 10s.
Tens.
10s, yeah, I think 10s is good. So 10, 20, 30, 40, 50, 60, 70. Now on the x's, my x's are only 0 to 4. We can just go by ones. Let's graph our points. 0, 0. The next one is 1, it's pretty close to 16, right? 15.9, it's almost 16. So I would put that right about there, in between 10 and 20. 2, 31.9, so a little bit above 30. 3, 47.8. So when we get to 3, it's a little bit under 50. And how can I tell this is coming out right?
The line straight.
Exactly, the points are all lining up on a straight line. That should always happen. 4, about 64. So 64, a little bit more than 60. Perfect. And there's your graph. Okay, if they don't line up straight, then something went wrong.
And guys, again, we'll just show you how to graph it. Tomorrow, when we ask these kind of problems, you're not going to have to graph them. We want to show you when you graph it, it does work out to be a linear function because it's a straight line. We just want to show you that so you understand. So we probably skip example 2. It's the same kind of thing.
Yeah, that's very similar. Would that be discrete or continuous? Read it over. It says M is the amount of money you spend. D is how many DVDs you buy.
You can't buy like a half a DVD.
Perfect, exactly. You can't buy a half a DVD. Yep. All right, let's look at this one. A cereal bar contains 130
Guys, we
calories.
skipped example 2, just so you know. On the back side.
It says the number of calories consumed is a function of the number of bars eaten. Okay. First, I want to know if this represents a linear function. Okay, and if you're not sure, let's make a table, because we already know what a table should look like that's linear. All right. Let's. What are the two things in this problem? Two variables. Bars and calories. Which one is independent? Well, bars, right. The number of calories depends on how many bars you eat. Calories depends. Calories is dependent. So let's do bars. That's going to be my X. Calories. That's my Y. And we don't have to do a lot. Let's just do up to like 3 bars.
3 bars.
If you eat 0 bars, how many calories did you consume?
0.
0. What if you have 1 bar?
100.
130. What if you have 2 bars?
260.
260. And let's do 1 more. 3 bars.
390.
390. Now, what's the rule when you look at a table to tell if it's linear? What do you check for?
Is it, I forget, is it the double one or is it the pattern?
You're looking for a pattern.
So you're checking if the x's are the same each time.
And do the x's add the same each time? Yep. Plus 1, plus 1, plus 1. Now, is there a pattern in the y's? How do you get from 0 to 130? You add 130. How do you get from 130 to 260? Add 130. 260 to 390. You add 130. Since we have a pattern, is that a linear function?
Yes.
Yes. If you can figure that out without making a table, that's fine. I'm not sure how you're going to do it without making a table, but that's probably the easiest way to do it. You could graph it and see if all the dots are in a straight line, but I think graphing is going to take longer. So that is linear. Find the domain of the function. So the domain, what letter is domain?
X.
X. So we're talking about bars. Okay. So think about the smallest number of bars you could eat.
0.
0. What's the highest number of bars you could eat? Assuming there's no limit, you don't have a limit on how many you have.
6 billion.
You can eat as many as you want.
What if your stomach explodes?
Yeah, eventually your stomach would explode.
I'm still.
So the domain, what did we say? What's the smallest amount of bars?
0.
0.
And the highest?
10 million.
Infinite.
Infinite. So that means you could eat any number of bars you want that's 0 or higher. There's no limit. So how would you write that?
0.
Any number that's 0 or higher. Greater than, how would you say that? The number of bars is what? Yeah?
Greater than?
Or equal to?
Infinite.
Well, what's the minimum amount? So you can eat any number from 0 or higher. That's your domain. The number of bars you can eat is any number 0 and up.
Is that a B?
That's B. Yeah, I use B for bar. You could use X. Could change it to X, but so the domain is any number 0 and up. Now, is this discrete or continuous?
Continuous.
Yes. Why is it continuous when you're eating a bar?
Because you can eat a half a bar for
Exactly. You could eat half of a bar. You could eat a quarter of a bar. You could eat a half an inch of a bar. You could eat any amount of the bar you want. You don't just have to eat the whole bar.
Yes, you do.
No, you can give it to someone else.
You were on a roll, Noah, then you just.
Yeah, maybe you can go down to this for that.
Yes, no, it's just.
Okay, so when you're eating something like a bar, I would say if it's something you could eat part of and save the rest for later, that would be discrete. Now, food can be a little tricky. Let's say you were eating like
Eggs.
Tic Tacs or something, something like that. I wouldn't say you could eat, in general, half of a Tic Tac. You don't take a Tic Tac, break it in half, and then put half of it in your mouth. So something like that is a little tricky, but if you're ever confused, you can ask me. So same thing with like a cake. Can you eat part of a cake?
Yes.
Yeah.
Yes, you could cut one slice of a cake. You could cut half of a slice, quarter of a slice. So if you're eating cake, you could eat any amount you
It's
want.
like a Ben and Jerry's pie.
I like it.
And
Yeah.
it's mostly fellow pie.
But you
want the
Especially.
But you do it anyways.
Now, when you graph this, how would that look? If you can graph any amount 0 or higher, would it be single dots with gaps, or would it be like connected? Yeah, it would be connected. So I'm not going to sketch it, but it would be connected. Okay? Continuous means when you draw it, it is connected. Continuous, connected. Discrete, gaps. All right, last problem.
We don't have example problem. Yeah, we don't have that.
It's okay, Zig.
You don't have example
I
5?
think we didn't talk about it last year either.
It's okay. So, can someone give me an example of the graph on the left? Think of something in real life that could be discrete. We can maybe make it fit into this graph. Yeah?
Height. Wait, is that going up or down?
The dots are going down.
Oh, your football skills? How about Xander's looks?
It's just cute. It's okay.
Well, I'll do something that's a little less offensive. How about,
Tapper.
I got one. How about if I had $6? If I had, and I only have dollar bills. I don't have anything else. I have 6 $1 bills. If I don't give any away to anybody, how many do I have left? I would have 6. What if I give 1 bill away?
You have 6.
No, if I give 1 away,
Bye.
I would have 5. What if I gave 2 bills away? If I had 6 and I give 2 away, I have 4. What if I give all 6 bills away?
0.
0. Now, could I give away 2.5 bills
Yes. Bill.
Yeah.
Unless you cut
You cut it in half.
without cutting the bill in half?
No.
I cut a
No.
dollar bill.
But what about change?
What if someone
The
has
actual
change?
bills will turn the actual.
I don't have any change on me. All I have is 6
$6
ones.
bills.
I had 6 $1 bills. Does everybody see how that's discrete?
I cut a dollar bill in half.
Okay. Any questions why that's discrete? How about continuous?
Well, you'd have to have
A
change.
Jen and Mary's pineapple.
Okay, let's deal with, think of ice cream. Sure, let's think of,
I was just talking about ice cream.
all right. So what if you had, let's say it's a company, or a restaurant, they have a lot of ice cream. They had 6 gallons of ice cream.
That's it?
If they don't serve any ice cream that night, how much ice cream is left?
6 gallons.
Now, what if they serve all the ice cream? What if they serve all 6 gallons?
Then you have 0 or 1.
Now, could they serve in between? Could they serve like 2.5 gallons of ice cream?
Yes.
Sure. Could they serve 2.7 gallons?
Yes.
Yeah. So that would be continuous. The more ice cream they serve, the less ice cream they have left in their freezer.
Well,
Understanding between discrete and
Yeah, it's
continuous.
Oh.
Yeah.
Alright.
Any question
Until today.
on the difference between the two?
There's not a ton of this stuff on the test tomorrow, a couple problems.
But I like this though.
You like it?
Yeah, because one's food and then one's stuff.
All right, so review worksheet. We're gonna give you guys time in
Guys, what
about.
we might do for the sake of time, so we can review a little bit in class, we'll probably just print it off for you. That way you guys have it. Then we can spend the last 15 minutes reviewing.
Yep.
Print it off for you and make copies.
So we'll print that.
Gonna do the gate.
Yep.
Yeah.
First test of quarter 2 tomorrow.
I feel something I was talking about.
Okay, brand new term, brand new chance to get your grade where you want
Okay,
it.
how long's the test?
The test is, I think,
14,
15.
14, 15 problems.
14, 15 problems. Okay, both Mr. Roy and me are gonna be after school today. Okay, we're both after school. So if you need us, come see us.
I think yours today.
Alright, so guys, you got some space.